Hey everyone, this is going to be a re-recording of the lecture from March 17th, and we went over section 7.3 through 7.6. Blackboard is being a little bit slow with uploading the lectures, so from now on I am going to record these live while we're doing lecture with my own software, and then I'm going to put it up on YouTube so that you can actually access it in a timely manner. So with that, let's get started. We're going to start with oxidation and reduction reactions. So if you are from a northern state, you are familiar with rust because your car, I came from Michigan, that's where I did my grad work, and the salt, the cold temperatures, the moisture, your car will rust. That is an oxidation-reduction reaction that I hope you never have to encounter. Other examples of oxidation-reduction reactions are the reactions that happen in our bodies to convert the food we eat to energy, and also all of your electronics. They have batteries. Those batteries are providing electrical energy, and that energy is coming from oxidation-reduction reactions. When you have an oxidation-reduction reaction, which I will probably for the remainder of the video call redox reactions, because that's a lot easier to say. It's a shorthand for oxidation reduction. So in a redox reaction, you're transferring electrons from one substance to another. So in this picture here, we have this compound A, and it has an electron associated with it. It's going to transfer that electron to B. As you can see on the product side, you have an electron on B. So these are our reactants. These are the products. If you lose an electron, you're oxidized. If you gain an electron, you've been reduced. And there's a mnemonic that you can use to remember that. It's called oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. So that's oil rig. Now I learned something different when I was in school. I learned about Leo the lion and how he says grr, which is very silly, but lose electrons. Sorry, my pen decided to do something weird. So lose electrons, oxidize, gain electrons, reduce. So that's Leo for lose electrons, oxidize, and GR for gain electrons, reduce. Whichever one makes sense to you, you can use it as a mnemonic to remember what oxidation means and what reduction means. So an example of a redox reaction is actually what has happened on the Statue of Liberty. So the copper metal, when it oxidizes, the copper oxide that's formed, it's green. So the Statue of Liberty was not painted green, that's just a chemical reaction. If you'll notice, we have the metal, the solid metal on one side, the copper. You know that it's a solid metal because there's this S here for solid, and there's a 0 for charge, so it is a neutral atom. You are losing electrons. This is the product side. So if you have electrons on the product side of a reaction, then that means that whatever you have something that's on the reactant side that was oxidized. In the second reaction at the bottom, the electrons are on the reactant side. So that means that oxygen was reduced. Oxygen gas is a diatomic molecule, so there's always two oxygen atoms. And you see this zero charge, which means that it's a neutral molecule. So to go from a neutral molecule to something negative, you have to gain electrons. To go from a neutral atom to something positive, you have to lose electrons. If you remember single replacement reactions, it's one of the reaction types that you're going to need to know. Single replacement means that you're replacing one metal with another. So if you have a metal that's more active than the other, you're going to get what's called replacement. In this case, the zinc is replaced by the copper, which is more active. So you actually get copper solid being plated onto the zinc plate. So that's another example. So let's do a quick learning check. I'll walk you through it so we can figure out which reactant is oxidized and which one is reduced. So I like to connect the two things that look alike. So I have silver here and silver here. I'm going from something that has a +1 charge to something that has a 0 charge. If you don't see anything up here, that means that you can imply that it's a 0. To go from +1 to 0, that means that we must have gained an electron. Gaining an electron means reduced. So the silver ion was reduced. Now, by process of elimination, since there's only two reactants, that means that the chloride ion was reduced, was oxidized. But if you want to look at the problem, we go from -1 to 0. So we have to lose an electron to get there. So it was oxidized. And I should have done that on this page to give myself more room, but I didn't. Mistakes happen. This is live. I think I did this with a live lecture on that day too. Oh well. We'll just draw a happy face because we're happy. Okay. Here's a real life example of a redox reaction in the body. So there are enzymes, which are proteins that do chemistry in your body. And sometimes they need molecules that help them do very complicated chemistry. And FAD is one of those molecules. It's called a coenzyme. FAD can be reduced, or you can have FADH2, and that can be oxidized. The way that happens is by transferring hydrogen. So the takeaway here is that transfer of hydrogen is redox. Okay. So if you are gaining hydrogens, you're gaining electrons. If you're losing hydrogen, then you're losing electrons. Another example of a redox reaction is when you are adding or taking away an oxygen. So your body can metabolize methyl alcohol. I would not advise it because all of the byproducts are also toxic to your body. So don't do it. But if for whatever reason your body is forced to do this, it can take methyl alcohol, which is right here, and it can form formaldehyde. Notice that you went from 4 hydrogens to 2 hydrogens. So we lost hydrogens. That means that we lost electrons. So we oxidized the methyl alcohol. Then the next reaction in this scheme is you take that formaldehyde and you add oxygen. When you add oxygen, notice how there's not a subscript here, which means that it's a 1. And now we have 2. That means that we have, again, lost electrons. Because we have to make a way for those extra electrons from the oxygen atom that's been added to glom on to our molecule of formaldehyde. And then you'll notice the same thing happens again, and we break up this formic acid into carbon dioxide and water. So we're losing more electrons. This is a summary slide of redox reaction characteristics. So when you're trying to classify something as being oxidized or reduced, these are the characteristics that you can look for. So oxidation always involves loss of electrons. So remember, this is the oil part of oil rig, or the Leo part of Leo the lion goes grr. You can also see oxidation as the addition of oxygen and the loss of hydrogen atoms. Reduction, which is the rig part of oil rig, and the grr, which is what Leo the lion says, it always involves gain of electrons. You can also see it as the loss of oxygen or the gain of hydrogen. So this summary slide will be helpful when you're doing homework because it lays out what you should look for to be able to identify a reactant that is oxidized or reduced. So we're moving away from classifying reactions, and now we're looking at some more math. We have these chemical equations and chemical reactions. We can actually take them and do calculations to predict how much product we're going to make. Before we can do that, we need to introduce some more math concepts. So we're going to introduce the mole today. The mole is Avogadro's number. Avogadro was a physicist, and he came up with this. 1 mole is 6.02 times 10 to the 23rd items. So that could be atoms. It could be molecules, any number of things. So when we start doing this, I will usually say number of things, okay? Avogadro's number is really, really big. 10 to the 23rd, that's a lot of zeros. I would like to have that in my paycheck. So that's Avogadro's number. 1 mole of something looks the same no matter what. It's always 6.02 times 10 to the 23rd. So if that's carbon, sodium, whatever, a mole of it is always going to be 6.02 times 10 to the 23rd molecules or atoms. We can use Avogadro's number as an equality. 1 mole is equal to 6.02 times 10 to the 23rd particles. And we can write conversion factors. So if we have moles over particles, then that means that we can convert something to figure out how much of it we have. So if we want over half is always what we use when we're multiplying by a conversion factor. This one, you're going to convert number of things to moles. For this one, you're going to convert moles to number of things. And we'll do some practice for that. This is dry ice, which is just solid CO2, solid carbon dioxide. If we have 0.500 moles of carbon dioxide, how many molecules do we have? Always start by rewriting the question. We have 0.500 moles, and what we want to know is how many molecules. We need a conversion factor. What we want is molecules at the end of the day. What we already have is moles. So that means our conversion factor needs to have Avogadro's number at the top and then moles at the bottom. You take that conversion factor and you multiply by the number of moles that we have. And we have 0.5 moles of CO2. When you do that multiplication, you should get 3.01 times 10 to the 23rd. When you put it into your calculator, what you're doing is 0.5 times Avogadro's number. And don't forget that times part, that's going to be your EE button, and that will get you into scientific notation, because you do not want to write all of these zeros out. You will absolutely make a mistake. We don't want you to do that. Let me get out the rest of my notes here. Sometimes I'm not prepared either. Okay, here we go. So let's do a learning check together. And this time, we're going to take atoms of sulfur and we're going to convert to moles. So for that, we're going to need to have what we want at the top, which is moles. 1 mole of sulfur over Avogadro's number, 6.02 times 10 to the 23rd, atoms in this case, because that's what we have. So we use this conversion factor along with our given information that we have 1.8 times 10 to the 24th atoms of sulfur. What you're going to put into your calculator is the 1.8 times 10 to the 24 divided by Avogadro's number. And again, make sure that you use that EE button. Some calculators may have EXP, but most nowadays have an EE button, and you may have to hit second function and then EE. So if you're still having trouble with using your calculator, let me know. When you do that division, you should get something in the ballpark of 2.990 moles There may be a couple more numbers after that. But we're not done. We only have 2 sig figs in our measurement from the problem. So we can only have 2 sig figs in our answer. For that, we have to round up to 3.0 moles of sulfur. And that would be letter B. So that was nice with elements. Now we're going to move to elements in a compound. So what's shown here is aspirin. I know everybody knows what aspirin is. Hopefully this lecture is not giving you a headache. Otherwise, you may need some. But we can look at the subscripts for each element in aspirin and say that aspirin has 9 atoms of carbon in one molecule, or we can say that it has 9 moles of carbon in 1 mole of aspirin. So these subscripts tell you relationships between the atoms in the formula. Let's write out a few more. So we had H8O4. We talked about the carbon. Now let's talk about how we can relate each of these to each other. So you have carbon, and you can have 9 moles, and this is in 1 mole of aspirin. With the oxygen, we said that it has a 4 as a subscript, so that's 4 moles. And the hydrogen has 8 moles. So if we're going to write these as conversion factors and use our 1 mole of aspirin, what you would write is something like this: 9 moles of carbon for every 1 mole of aspirin, which is C9H8O4. And this you can use to figure out how many moles of carbon you have in a given number, number of moles of aspirin. So let's do one. Here, the question is asking how many atoms of oxygen are in 1.50 moles of aspirin. So we have moles of aspirin, and we need to somehow get to the number of oxygen atoms. That's our question. What we can do is go from moles of aspirin to moles of oxygen, and from moles of oxygen to atoms of oxygen. For this first part, we need a mole relationship. We need an equality. We need a conversion factor that's going to tell us how many moles of oxygen there are for every mole of aspirin. Then once we have moles of oxygen, we need to use Avogadro's number to get from moles to atoms. So we're going to start with the mole relationship. We know that we have 0.150 moles of aspirin. What we want from this is moles of oxygen on the top. And we want to be able to cancel the moles of aspirin, which I'm just going to abbreviate here. When we look at the chemical formula for aspirin, we see a 4 as the subscript, which means that there's 4 moles of oxygen in every 1 mole of aspirin. So this is our mole relationship. Now we need to go from moles of oxygen to atoms of oxygen. What we want needs to be on the top. That's atoms, which is number of things. So we're going to put Avogadro's number at the top. And then we're going to put 1 mole of oxygen at the bottom. That will get rid of our moles. So we start with moles of aspirin. We cancel that out. Then we have moles of oxygen, and we cancel that out. You're going to see the screen covered up a little bit when I'm changing colors. And we're left with atoms of oxygen. When you do this in your calculator, you're going to take the 0.150 multiplied by 4, and then multiply that by 6.02 times 10 to the 23rd. When you do that, you should get a number like this. But we have to look at sig figs. We have 3 sig figs in our measured amount of aspirin. So we should have 3 sig figs for our answer. And that's 3.61 times 10 to the 23rd atoms. So we know how to use Avogadro's number, hopefully, or we're going to practice. Now we're going to build. We can have a compound or an element. We know that we can have some number of moles of that element, but how much does that weigh? We're going to talk about the concept of molar mass. So molar mass is the mass of 1 mole of something. So it could be an element, could be a compound. For the element, it's the atomic mass expressed in grams. So for a mole of carbon, you would look at your periodic table. Up here, this 6 is your atomic number. So that tells you how many protons you have. And this decimal at the bottom is your atomic mass. That's where you would get your molar mass if you're dealing with one element. If you're dealing with a compound, we're looking at the sum of all elements and their molar masses. So let's practice that. This is just a visual of what 1 mole looks like. It's going to look different depending on what the molar mass is. So let's calculate a molar mass of a compound. We have lithium carbonate, which is used to treat bipolar disorder and some other mental disorders. And what you have to do is figure out how many lithiums you have, how many carbons you have, how many oxygens, and then you total everything up. So your molar mass is going to be equal to all of the lithium plus all of the carbon plus all of the oxygen. For the lithium, we see that there are 2. So we're going to take the molar mass of lithium, which is 6.941 grams per mole, and we're going to multiply it by 2 because there are 2 lithium atoms in this compound. We're going to add to that the molar mass of carbon. There's only 1 carbon here, and I'm writing it out. When you're doing it, you don't have to. But there's only 1 carbon atom, and its molar mass is 12.011 grams per mole. For the oxygen, there are 3 because of the subscript. So we're going to multiply 3 by the molar mass of oxygen. When you total all of that up, you should get something like 73.863. That's a bad 6, y'all. Grams per mole. So grams per mole is your unit for molar mass. Let's do another one. So we have the molar mass of this compound that has carbon, hydrogen, and oxygen. So we're going to look at our periodic table and figure this out. We've got 2 carbons, so we're going to take the molar mass of carbon and multiply it by 2. We're going to add to it 6 times the molar mass of hydrogen because there are 6 hydrogen atoms. And we're going to add to that the molar mass of oxygen. Because there's only 1, we don't really have to do any multiplication there. So you add all of that up, and what you should get is something in the ballpark of 46.069 grams per mole. You cannot do this without your periodic table unless you just happen to know all of the atomic masses of all the elements. So we know how to calculate molar mass. We know how to use Avogadro's number to go from moles to number of atoms or molecules. Now we're going to combine these concepts, and we're going to be able to convert between a mass of something in grams to moles and vice versa. For this, we're going to take that molar mass and we're going to write an equality. 1 mole of something is equal to its molar mass. In grams. So that's going to be the conversion factor. The molar mass, you calculate. Let's work a problem to make it make a little bit more sense. We have table salt. Everybody knows table salt. Your mama, your grandma probably has a box of Morton's iodized salt right now. I know I have a box on my shelf. It has a weight associated with it. If you really wanted to, you could figure out how many moles of sodium chloride are in that box. should not have gone forward. We need to figure out the problem first. So I'm going to insert a new page here. We know that our box of salt has 737 grams in it. And the question is, we have all this salt. How many moles do we have? What's our plan? First, we have to calculate our molar mass. In this case, we're calculating the molar mass of NaCl. Then, we're going to use the molar mass, which I'm going to abbreviate MM, as a conversion factor. To go from grams to moles. So for the first part, we need to calculate our molar mass. You look at your periodic table, you find sodium, and the molar mass of sodium is 22.990 grams per mole. There's only one atom of sodium, so we don't have to do any kind of multiplication there. To it, we're going to add the molar mass of chloride ion, and that is 35.453 grams per mole. When you add those two together, you get 58.443 grams per mole. And this is NaCl. Now, we can write out an equality. 1 mole of NaCl is equal to 58.443 grams per mole. Grams of NaCl. You don't have to write the per mole. So we need a conversion factor to go from grams to moles. If what we want is moles, that means that has to be on the top of our conversion factor. So we're going to take moles, which in this case from our equality is just 1 mole of NaCl over 58.443 grams. That 8 is a little sad. I'm going to try to make it a bit better. There we go. You're going to take that conversion factor and multiply by your 737 grams of NaCl. Your grams cancel. So you should be left with moles. When you do this, you're going to put into your calculator 737 divided by the 58.443, and you should get something like this, 12.611 moles of NaCl. Unfortunately, your calculator does not tell you sig figs, so we have to go back to the problem and look at what measured value we were given. That's the mass of the salt, and it has 3 sig figs. So our answer needs 3 sig figs. So we're going to round that to 12.6 moles of NaCl. That's a lot of salt. Don't use it all at once. We'll do another problem as an example. So I know in real-time class, I had you guys do the problem, and then I did the problem, but obviously can't do that right now. So I will do it for you. In this problem, we have 59.8 grams of water. That's our sample. And we want to know how many moles of water do we have. First, we have to calculate our molar mass of water. That molar mass is going to be, since we have 2 atoms of hydrogen, we're going to say 2 times the molar mass of hydrogen plus the molar mass of oxygen, which is 15.99. If you round to 16, you'll still get the same answer pretty much. When you do that, you should get something in the ballpark of 18.015 grams per mole. Now we need to go from grams to moles, and we're going to use a conversion factor. Our equality says that 1 mole of water is equal to 18, ooh, that's a bad 8. My tablet does not like circles. So 18.015 grams of water is the same thing as 1 mole. So we have to put what we want at the top of our conversion. And in this case, we want moles. So we're going to put moles of water at the top. On the bottom, we're going to put that calculated molar mass, 18.015 grams of water. That's our conversion factor. We take that and we have to multiply by our sample size. Our grams should cancel, so we're left with moles of water. When you do this, you're going to put into your calculator 59.8 divided by 18.015. When you do that, I'll give you a second to do it in your calculator, just to make sure you're alive and with me. But always make sure that you're doing division when you're converting the grams to moles. Otherwise, you will get a large number that is not the correct number. So you should get 3.319 with some other numbers coming after it, moles of water. Now we need to take into account sig figs. We've got 3 sig figs in our measured amount, so that means we need to have 3. So we need to round this 1 up to a 2. We say 3.32 moles of water. That's it. This is a concept map that will help you put together how you get from one thing to another. So for example, if you need to go from grams of something to atoms, you would have to use the molar mass to go from grams to moles, and then Avogadro's number to go from moles to atoms. So this chart may help you when you're looking at the problem and you know what you have and what you're trying to get to. So try to use it. If it doesn't make sense, then just go back to the sample problems that we did, and that should help you set up your homework problems and your quiz problems. So good luck. I hope this helps you. And again, From now on, I'm going to post these lectures on YouTube so we don't have to worry about how long Blackboard takes to upload the lectures. Have a good one. See you soon.